So last time we finished looking at monads, and I promised to you that we will look at one example of a categorification process. Yeah, so generally, I mean, the simplest kind of algebraic structure that we have is that of a monoid. I mean, that is enough categorical. Yeah, we have one particular set now with a specific element. Yeah, so it's a non-empty set together with a binary operation for which that element is identity. Categorification is a process in which we replace sets by categories, elements by objects, and the identities that they satisfy. I mean, some operations, yeah, binary operations or ternary operations, any operations by functors of same arity. And finally, whenever we have equality, then that equality we replace by isomorphism, a natural isomorphism of appropriate kinds. So that's categorification. We are going to categorify the simplest concept, that is of a monoid. And such categories are called monoidal categories. And once we do that, then our next job would be to use these monoidal categories in some specific way. So for example, I mean, I also want to give you some motivation for what we are going to do with these. So normally, if you consider a locally small category, which has been our assumption for several important theorems. Locally small category means that our home sets are actually sets, and the composition is like it respects set composition. Composition in the category respects set composition. However, if you go to, let's say, the category of abelian groups, and you fix two abelian groups G and H, then you can also and take two, let's say, take two group homomorphisms from G to H, F and G. Then you can add F and G pointwise, right? F plus G of X is F of X plus G of X. Then you can also define a zeromorphism in that home set. Yeah, I mean, there is something known as zeromorphism, which takes every element of group G to the element 0. So constant 0 function is a group homomorphism. Similarly, for F, there is minus F. Yeah, F plus minus F is equal to 0. So it carries some extra structure. It carries the structure of an abelian group. Moreover, the composition of group homomorphisms is a bilinear map with respect to this addition. Yeah, it distributes, like the composition distributes over addition on both sides, left and right. So we have to capture this property, this extra structure on the home set appropriately, and that we will do using monoidal categories. So our purpose is twofold. One is to learn categorification and then do the enriched category. Okay, so what is a monoidal category? As I said, so I mean, the notation that we borrow is the tensor notation. Yeah, the bifunctor that we are going to work with is going to be denoted by tensor, like tensor in appropriate module categories or category of algebras. So those things, they also satisfy these properties. So let's write the notation. So a monoidal category is a tuple C, then tensor from C cross C to C, then we have I have to describe all these things, is a tuple of data consisting of okay, a collection, oh sorry, I mean consisting of a category C, yeah, then a bifunctor. What is the meaning of a bifunctor? Can you tell me? Its domain is a product, it's just a functor. So whenever you fix an object in one component, then also it is a functor. Okay, a bifunctor. Then I is a specific object in C. Okay, and apart from that, we have got natural transformations alpha, okay, from okay, what should I say here? Natural transformation alpha with components alpha ABC from A tensor B tensor C, and look at this notation, what I am writing. I am writing an arrow and I am making it an isomorphism. So natural transformation alpha with components this indexed by A triples of objects of C. Okay, then a natural, I can say natural transformation or natural isomorphism directly. So can you tell me what this particular natural isomorphism is trying to capture? Associativity. Okay, so but we call it the associator. Okay, then a natural isomorphism left uniter lambda with components lambda A from I tensor A to A, and right uniter, so natural isomorphism right uniter rho, and how do you remember left and right? Lambda starts with L and rho starts with R when you write them in English. Yeah, so with components rho A from A tensor I isomorphic to A for A in object C, for A in object C. Okay, can you tell me, like I have written natural isomorphisms, but what are these isomorphisms between? Which functors? For example, let's do the left uniter. Yeah, what is it an isomorphism between? Which two functors are we talking about here? I tensor blank and identity. Yeah, so that you understand. And similarly, what is the what about alpha?
Tensor composed with
No, identity comma, maybe I should try to write it down, yeah, because so it will be C cross C cross C, C cross C, and then C, and C cross C. What is the first one? Identity. Well, let me just write this, tensor, and this is tensor. And the other one is tensor times identity, and then tensor. Okay, so there are two different natural transformation, two different functors here, because there are two different sides of the commutative square. But of course, like this square doesn't commute up to equality, it commutes up to alpha. That's what we are talking about. Alpha is a natural isomorphism, and always you remember that natural transformation means it consists of the data indexed by objects of the domain. So that's precisely what we are doing here. Okay, so fine. Any questions here in this definition? Okay, so everything is like the same. Natural isomorphism, if you take to be identity, then we will say it's a, so maybe that's a note that you should have. So note that if alpha, lambda and rho are equality, are replaced by equalities, then we say that C tensor I mean we usually just write this, is a strict monoidal category. Strictness means everything is happening up to equality. Yeah, we don't need to keep track of this. Okay, my definition is not yet complete. Yeah, if we are writing associativity, then we also have to talk about the coherence of associativity. Then identity should do what identity is supposed to do, right? So all these conditions, my definition is not complete. Yeah, so satisfying, so this is the data, the following conditions. Okay, so first one, we have to talk about this. So this is the famous pentagon diagram. Okay, so A tensor, B tensor, C tensor D. Okay, so we are just going to change parenthesis. Yeah, and ultimately we plan to arrive at this particular location. So A tensor B, then tensor C, tensor D. Now, can you tell me a sequence of morphisms so that we can arrive at this? We have to simply change the parenthesis, and we can change parenthesis like of 3 components at the same time. That's what alpha does. Very good. Identity comma alpha. So let me write that. So 1 sub A tensor alpha B C D. Okay, and this is going to A tensor B tensor C tensor D. Okay, then
What is meant by tensoring of morphisms?
it's just preserving the same thing. I mean,
Universal property involved?
no, I mean in each of the individual components, it's a bifunctor, right? So it's a bifunctor, so we are doing it component wise. Yeah. Then A tensor, yeah. Very good. So alpha A comma B tensor C, comma D. Right. So that will land me inside A tensor, B tensor C, okay, and tensor D. And from here, can we go there? Alpha A comma B comma C tensor 1 sub D. Very good. And there is another way, obviously.
Inverses involved.
Which inverses?
Like the first morphism should be alpha inverse, and then I think the three of these are alpha inverses.
No, they are all alphas as far as, see, alpha is bringing the parenthesis in the front. Yeah, another one from here to here. If we, alpha A comma C tensor D. Yes, C tensor D is a new object, so that can be used. And we will get A tensor B tensor C tensor D. And from here to here, now we have something. What should we do? Alpha A tensor B comma C comma D. Okay, so that's how, like, this is a pentagon. So this is the famous pentagon diagram. Yeah. So these are following like coherence conditions. So this is a coherence condition, first one. And what is it trying to say? That whenever we are doing it with multiple things also. So for example, you can conclude that if we have any particular like 5 tuple of objects, then also you can do the same thing and you will arrive at the right thing. You have 2 different ways of going from one particular parenthesizing to another parenthesizing, but they are the same. So that's what is called a coherence condition. Yeah, I mean, this is a coherence condition. There will be one more. I mean, something for identity. Can you tell me what the identity should do, what the coherence conditions for identities are? We are just going to draw many diagrams today, many big diagrams, but they are all obvious.
A tensor, I tensor, B.
Correct. So A tensor, I tensor B, and I am always going to write parenthesis on the right so that we can apply it appropriately. Then we will have A tensor I, tensor B, and then over here what do I have? Alpha AIB. Okay, A tensor I tensor B. Here what do I have? I have to go down to A tensor B, and this is 1 sub A, tensor lambda sub B. Okay, and over here it is rho sub A, 1 sub B. Very good. Okay, so this is the other identity, like, so they are compatible with each other. Whatever we do, yeah, it makes sense. Okay, then so this is our definition of a monoidal category. It looks very long, like a very long definition, but it's really not. Yeah, it's a simple enough thing. Everything we are categorifying. Once you understand the flavor of categorification, then things are simple from that point onwards. What is important in this case is finding out these coherence conditions. Because the theorem, yeah, so this is Maclane's coherence theorem. I'm just going to state it without being precise. You can look it up in Maclane's book if you are interested. So, Maclane's coherence theorem. Okay. So, every formal diagram formed using alpha, lambda and rho commutes. Okay, so formal diagram I haven't defined it, but you can imagine what it should be. So for example, if we have a phi tuple of objects, and then in that phi tuple you have specified some kind of bracketing and another bracketing or another parenthesizing. So those two objects are isomorphic. Yes, because the order of the objects is the same. So they are isomorphic, and you have to show that using some combinations of alpha, lambda and gamma, alpha, lambda and rho. So that is possible by using just these basic coherence conditions. You don't need anything extra. So basically, all the relations that the meaningful natural isomorphisms one can hope, the generators for them are just these two diagrams. Yeah, any meaningful natural isomorphism is generated using this. That's what we mean, like the meaningful part is captured by this formal diagram. I believe there is an error in MacLane's book. MacLane actually tried to sell this idea, and then he said every diagram formed using this alpha, lambda and rho commutes, but that's not true. Yeah, there has to be some conditions on the diagrams formed. Yeah, if you are interested, you can look up some stack exchange problem, yeah, where you will find that particular diagram which is not formal. Yeah, so it doesn't commute. Okay, I mean definition itself is like definition alone is useless, so we have to look at some examples. Okay, so what are the, can you give me one example, one simple example? A monoid, very good. How? A monoid thought of as what? A monoid thought, single object category. Thought of as a functor category. No.
Like C2C, the category of endofunctors.
No, we are not doing that. Okay, I mean a monoid is a slightly involved example, so I will say a discrete, a monoid thought of as a discrete category whose objects are elements of M. I mean a monoid M thought of as a discrete category whose objects are elements of M. So see, you have to understand something. There was some issue with the example that you gave, a monoid thought of as a single object category. Look at this. You are given the data of a category and then a bifunctor on it. If you think of a single object category, single object small category, let's say, which is a monoid, but then there is no external piece of data present over there. You understand? We have to provide this tensor as a bifunctor. And so it's an external piece of data. So therefore, monoid thought of as a discrete category whose objects are elements of M and whose operation is the bifunctor. Okay, this is a strict monoidal category. Do you agree? The only isomorphisms in this category are identities. Oh, I mean, so therefore, you have a strict monoidal category. But try to understand the difference between internal operation, that internal operation in a single object monoid that is obtained by composition. But composition is not the operation, the bifunctor is specified here, that's external. So therefore we have to do it this way. I will come back to a single object monoid, single object category, but let's look at some more standard example, because this single object example is a bit involved. Okay. So I'll give you another example. So the category of sets together with a cross product and identity element is singleton. Identity object is singleton. So cross product is a bifunctor. Yeah, I mean, if A is a set, then A cross blank is a functor from set to set, and similarly blank cross A is also a functor from set to set. So it is a bifunctor. However, now what do you know about sets? Like, why do we need this alpha, rho and lambda? Is A cross singleton equal to A? No. It is isomorphic. But not only that, it's not just isomorphic, it is, though these two objects are isomorphic up to a unique isomorphism, thanks to the property of, the universal property of product. Right? So therefore, you naturally get the left unitar, you naturally get the right unitar, you naturally get associativity like A cross B cross C and A cross B cross C. These two objects are obviously isomorphic, and they are also isomorphic up to unique isomorphism, and that unique isomorphism is captured by the data of alpha. In practice, okay, we do not really talk about this particular morphism alpha. I mean, we do not have to describe, explicitly describe that morphism alpha. You understand? It is obtained from the universal property. There is a unique natural isomorphism. So whenever we are taking, for example, this particular alpha ABC, where tensor product is cross product, well, we know what it should be. Yeah, we know what it should be. So that is the component of this. And such components, such component morphisms, such component isomorphisms, they will constitute one natural isomorphism as shown in that diagram. Okay, so alpha here was, I mean, just to complete, so alpha was from this composition to this composition, right? Okay, so similarly, I mean, what was the role of cross in sets? Cartesian product is the name, but what was the role of cross? It is a product. So in general, if you have any category which has products, finite products is sufficient. We don't even need infinite products. So, or generally, any Cartesian category with products, with binary product and terminal. Okay, so you have this example. However, the monoidal category, the bifunctor, doesn't really distinguish between limits and co-limits. So the third kind of example that we have is sets with disjoint union and empty set. So disjoint union is what in the category of sets? Co-product. So I can write, or generally any co-Cartesian category with binary co-product and initial object. Initial object will be the identity for this bifunctor. Yeah, obviously. Okay. Another thing like that we have been using already. Yeah, I mean, I just want to point it out separately, that the category of all small categories and cross product with respect to a single object category, single object discrete category. I can write it as just one. Yeah, this is a special case of two, really. Yeah. So another thing, like I'm just going to write some more examples to emphasize on what we are doing. In abelian groups, what is the binary product? Direct sum. And what is binary coproduct? Direct sum. Both of them are direct sum. Yeah. So ab, direct sum, and then 0, or category of R modules with direct sum and 0. Yeah, these monoidal categories are really important. So that's why I'm explicitly writing them. Okay. Then in general, you can also talk about a lattice or a semi-lattice. Yeah, so lattice or a semi-lattice is with respect to either join or meet, whatever is available. Yeah, I should say bounded. Yeah, bounded lattice or a semi-lattice, which is either with respect to either join or meet, is, it is what?
It is just the Cartesian example. Right?
Cartesian example, correct, yes. But I just wanted to say that is a strict monoidal category. Yeah, this is strict because no isomorphisms are required, everything is happening up to equality. We are just talking about elements. Okay, the seventh example is actually interesting. We have already discussed that, but let's discuss it in detail. So, a commutative monoid thought of as a single object category. Okay, so commutativity is extremely crucial in here. Now, why is that the case? Yeah, so suppose, so I'm going to prove one theorem here, and theorem, this theorem is called Ekman-Hilton argument. This argument given by Ekman and Hilton, obviously, it works with very minimal assumptions. Okay, so okay, this is a word probably that you haven't heard. It's magma. A magma is a set, non-empty set, together with a binary operation. Associativity is not required. If it is associative, then you call it a semigroup. If that binary operation has identity, then you call it a monoid. So this is a magma with an identity. Okay, so suppose X is a non-empty set with two binary operations I am going to call one of them this circle and another one tensor. with identities 1 circle and 1 tensor respectively, satisfying this transfer law. What is the transfer law? That A tensor B composed with C tensor D is equal to A composed with C tensor B composed with D for ABCD in X. Yeah. Then both the operations coincide and this unique operation is commutative. Okay, so a very beautiful result, and the proof will make you feel like an undergraduate again, first or second year undergraduate, first course in group theory, yeah, abstract algebra. By the way, I mean, before I give you the proof is quite simple. I want to explain the importance of this Ekman-Hilton argument. So this has its origins in algebraic topology. Like, I hope most of you have seen the fundamental group construction. What is the fundamental group called? What is the notation? Pi 1. Yeah, so pi 1 associates to any pointed space a group. And pi 1 is actually defined to be the set of homotopy classes of loops at the base point with respect to appropriate composition. Yeah, composition up to homotopy. Now, loop is what? A loop is nothing but you take an interval and then you have a continuous map from this interval into your space capital X such that both the endpoints, they map to the base point. That is a loop. Now, if instead of this loop you take I square, the interval I, you take I square, so 0, 1 square, 0, 1 cross 0, 1. Then you do the same process like the set of all maps from x cross 0, 1 square to x, which take the boundary of the square to the base point. Then you take homotopy equivalence classes appropriately, you will get pi 2. And similarly, if you take 0, 1 to the power n, then you will get pi n. Okay, so this Ekman-Hilton argument is lies at the heart of the proof that every pi n for n bigger than 1 is abelian. Okay, so all higher homotopy groups are abelian groups. Only pi 1 is allowed to be non-abelian, the others are not. Okay, so this is an argument in 1930s. In fact, I read some story that Edward Czech, yeah, we have seen stone Czech compactification. So Edward Czech came up with a proof of some result, and then these two people, they did not let him publish his proof, and then they minimized his importance to a single paragraph in the proceedings of that conference by providing this argument. Okay, so let's see, this argument is quite simple. Okay, and this unique operation is commutative as well as associative.
So, in higher homotopy groups, what these are two operations?
Well, I don't want to get into that. Yeah, you can check it for yourself. This is not a topology class, but I just gave you the motivation. Right. So, Yes, so you are not even assuming associativity or anything, okay? Everything is just happening. Everything is coming for free at the cost of this transfer law. Okay, so let's write this. So one circle is equal to one circle composed with one circle. That is the definition of the identity. It is a two-sided identity, which can be written as one tensor one circle, composed with one tensor one circle tensor one tensor. Then you obviously use the transfer law. So then that will become one tensor composed with one circle tensor one circle with composed with one tensor. Well, what is that?
One tensor.
It is one tensor, yes, one tensor, because one circle is identity for circle. So one tensor composed with one tensor, which is equal to one tensor. So the first thing that we show is that it is identities are the same. Okay. Then A circle B is, now I can just use one. Yeah, one is the identity for both of them. So one tensor A, circle B tensor 1, which is same as one circle B tensor A circle 1, thanks to the transfer law, and that is what? Yes, this is B tensor A. So now we have shown that A circle B is B tensor A. Okay, but let us not stop here. We can use B circle 1 tensor one circle A. Okay, so that again we will use B tensor 1 circle 1 tensor A, which has to be, okay, so done. This shows commutativity, and similarly you can complete the proof for associativity. Yeah, you have been given enough directions. Yeah, so it's a very simple argument. Yeah, but this Ekman-Hilton argument. So now okay, let's come back to monoidal categories, because that was our main purpose. So a single object category, small category. Okay, let me highlight that it is a small category. Single object small category has got two operations. Circle is composition. There is only one object. Yeah, so object to object bifunctor is not doing anything. You just have to worry about the morphism to morphism. So morphisms are these elements of X. So composition is our circle operation, and the tensor operation is given by the bifunctor. So whenever you try to impose another operation on that, and it is a bifunctor, so because it's a functor in each component, it must satisfy the transfer law, right? So that's the only thing that we needed to check. So now both these operations must coincide, and it becomes a commutative monoid. So non-commutative monoid cannot be thought of as a monoidal category, single object monoidal category. Any questions?
So this bifunctor will be
Mhm.
from the category of arrows, cross the category of arrows to the category of arrows.
Bifunctor will be from the single object category cross single object category to single object category. Why category of arrows?
But then the composition is from home set cross home set to home set. So the bifunctor should also be on the same set from home set.
No, but you already have just compositions in the category itself. In each component, like if you fix one component, then in that component the composition has to be preserved by the bifunctor. So that's what this transfer principle is.
We have two operations. One is the arrow composition in the single object.
Yes.
Category. So the arrow composition is a function from home set cross home set to home set.
See, look at this. Look at this particular side. A composed with C. That is a composition in your category. And B composed with D is another composition in your category. And where will the tensor of this will go? Well, it will go to this composition, because that's the definition of a bifunctor. So therefore the transfer law is satisfied. Okay. So this is Ekman-Hilton argument, and we have seen enough examples. Yeah, I mean, monoidal categories, there are plenty of examples. Huh? So non-commutative monoid, you can fit it into example 1. You can treat it as a discrete category whose objects are elements of M. Yeah, and like it's an external operation. But if you want a monoid as a single object small category, then it will automatically turn out to be, like if it is equipped with a monoidal structure, then it will turn out to be commutative. Okay. So there are some associated notions. Now that we have defined a new type of category, we will also have a new type of functor. So what is a monoidal functor? I mean, I am just going to define for this class, I will just define a strict monoidal functor. Okay, so you have got C, tensor C and IC, and a monoidal functor F from this monoidal category to another monoidal category, yeah, is a functor F from C to D such that F of A tensor CB is equal to FA tensor D FB, and F also preserves the identity object. Okay, so why I am calling it strict, you can understand. I am saying these objects are equal. Yeah, otherwise you can also have a weak monoidal, like just a monoidal functor, but yeah, I mean, you can guess what it is. You have to replace it with isomorphisms and some data. Okay, so in practice, yeah, whatever monoidal operation that we think of, most of these, for example, sets with Cartesian product, this operation is not just monoidal, but it is symmetric monoidal. A cross B is isomorphic to B cross A. Yeah. Sometimes it also satisfies a slightly weaker condition called a braided monoidal structure, but I am going to ignore that. I just mentioned it. It's slightly weaker than symmetric monoidal structure, but I will ignore that. So, yes, symmetric monoidal category. So, obviously, it has one extra piece of data. You have C, tensor, I, alpha, lambda, rho and S. Yeah, where, I mean, I am not even defining it properly, where SAB is a natural, is the component of the natural transformation S from A tensor B to B tensor A. Okay, so that's all, which satisfies the structure only gets one additional natural isomorphism S, but it satisfies something more, that whenever you have A tensor I and then you have I tensor A, and then here we have A and here we have A. What is this? A tensor I to A, rho A. This is lambda A and this is SAI, not alpha, SAI. The symmetry, natural isomorphism. Yeah, I mean, obviously you know this. But we are not doing anything different. Then what else? Then we will have this particular diagram. Well, we have A tensor B tensor C. From there we can go to B tensor A tensor C. Okay. Then from here we can go to C tensor B tensor A. This is the exact opposite, and there is another way to reach here. Yeah, you first do, no, you do this A tensor B tensor C. From here you have applied alpha over here, then you apply the symmetry. Then again you apply associativity. Yeah, this is B tensor C tensor A. Sorry, I think I have made a mistake here. I should have said something different. Here B and AC. Yeah, B and AC. And from here we are coming to this. Yes. So this is alpha ABC. Then this one is S A comma B tensor C. Then this is alpha inverse. Yeah, it looks like alpha inverse, right? Alpha inverse BCA. Then this one looks like, that's SAB tensor 1C. Then over here that is associativity inverse. So alpha inverse BAC. And over here we have alpha no, not alpha. This is 1 sub B, yes, 1 sub B tensor SAC. So this diagram is required to commute, and finally that SAB is its own inverse. Right, so that's also important. So we write it like this: A tensor B, and this is equality, and we have B tensor A in between. So SAB, and this is SBA. Right, so that's all. So these three additional diagrams have to be added to our generating set of coherence diagrams, and then everything will make sense. So this is a symmetric monoidal category. Okay, like there are different types. So the braided monoidal categories, they have a slightly weaker condition that there is some morphism, but it is not its own inverse. So SAB composed with SBA is not necessarily identity. But braided monoidal categories are quite often used in theoretical physics, in particular quantum field theory. So monoidal categories were actually introduced like mainly for the purpose of doing theoretical physics. Mathematicians, I mean, nowadays they study, but in the beginning, mathematicians were not so much interested in this, apart from this coherence conditions. But physicists need them in string theory or some version of gravity. I'm very bad in physics. Okay, so there is another type of a monoidal category which is favorite for computer scientists. Like if you have done, if you are a computer science student, then you should learn category theory to learn about this particular type of category, and that is called Cartesian closed category. Or as they like to call it, CCC. This is used in function level programming, okay, because types are the objects here and you need some version of currying and uncurrying. You remember currying, uncurrying from adjunctions. So adjunctions are the key here. So I mean, okay, maybe I should define, like this is saying something more. This is saying it's Cartesian plus it is closed monoidal. Okay, with respect to Cartesian monoidal structure. So what I really need to define is what is closed monoidal. Closed monoidal structure, yeah, correct. So closed monoidal category so this one has one additional property, that for any object A in A of C, I mean it's a monoidal category first of all, with this additional property that for any object A of C, the functor blank tensor A from C to C has a right adjoint. Okay, this right adjoint, which is usually called the internal home functor. Internal home functor. And denoted bracket A blank from C to C. Why internal home? Yeah, I mean, so can you give me an example of a CCC? Sets. Sets are modules? Really?
Okay, home is also a derivative.
No. I mean, unless it's
By
commutative. So let's not go into algebra side yet. But closed Cartesian closed category is sets. Yeah, for example, sets with product and singleton is a CCC. Why? Because blank cross A, for blank cross A has a right adjoint, namely home, I mean sets A blank. Yeah, we have seen this home and currying, uncurrying adjunction. Yeah, let me remind you if you have forgotten that the home set from B cross A to C in the category of sets is in natural bijection with the home set from B to the home set. Like this is the way in which we can replace a two variable function by a one variable family of one variable functions. So that's why it's used in programming. Yeah, if you want to deal with functions with higher arities, then this is important. Usually type theory, yeah, single type lambda calculus, yeah, that also comes under this. Any questions about this? Okay, I should give you some more examples. Well, another example just for the sake of it, it's just finite sets. Yeah, you are not changing anything there. It's a subcategory of the CCC sets.
So the right adjoint is defined up to unique isomorphism.
Right adjoint is unique. We have shown that.
Unique up to unique isomorphism.
Yes.
While the monoidal structure requires certain coherence conditions which are equalities. So, are there coherence conditions for this right adjoint? Like which one among these?
No, we do not ask for that. Like, do not ask for compatibility of this right adjoint structure with the monoidal structure. Yeah, we just need that this exists. Whenever this exists, yeah, I mean, there is something important. Like, this is an adjunction, okay? Look at this, the co-unit of this particular adjunction. What does it do? Co-unit is epsilon. It takes, I mean, b to the power a, and maybe I'm not writing it correctly. I should write it in this language. C to the power a cross a. This is also called exponential. Yeah, to C. What does it do? It's the evaluation map. It takes a function from A to C and an element A in A and maps it to f of A. So the co-unit is actually the evaluation map. And you can use this adjunction to show a lot of properties. Yeah, I mean, where C to the power A is the home from A to C or sets from A to C. You can prove all the properties of exponential. Yeah, A to the power B cross C is A to the power B to the power C. Then A to the power B disjoint union C is A to the power B multiplied by A to the power C. All the properties of exponential, they can be obtained via this particular adjunction. But we are replacing like all the numerical properties, arithmetic properties of the exponential function, you can obtain them for sets. Okay, there is one very beautiful example of this, of a Cartesian closed category, and that will also introduce you to a new subject, and that is, no, I am going to say first Boolean algebras. Okay, some Boolean algebras, like we have B, then we have meet, we have join. It's a lattice, basically. It's a bounded lattice which such that every element has negation, and it's a bounded distributive complemented lattice. So, bounded distributive you can write, yeah, meet distributes over joins, join distributes over meet, both ways. Bounded distributive lattice with complements. So complement does what? Yeah, I mean, think about power set of a fixed set. It automatically has the has complements. Yeah, so basically we are saying this. So A meet negation A is 0 and A join negation A is equal to 1. So negation A is the unique element which satisfies these two properties. The uniqueness of negation A can be obtained from other properties, yeah, bounded and distributivity. Okay, so Boolean algebras in particular, I mean, I will give you an example. If you have never seen Boolean algebras, then power set of any set X, intersection, union, empty set, whole set X and X minus blank. Yeah, the complement operation. So this is a Boolean algebra. Okay, in a Boolean algebra, there is also an implication defined. The implication arrow, how is it defined? Like, so A arrow B is defined to be, in a Boolean algebra, negation A or B. Yeah, I mean negation A or B. So, this particular arrow, yes, so now I can write. So, we have from B to B, I have two functors. First one is blank meet A. Yeah, meet is the product in any lattice, meet is the product, so it's Cartesian, and it has a right adjoint, namely A implies blank. A implies blank is given by this. So, this is also a Cartesian closed category. In fact, a small such small and skeletal category. More generally, yeah, there is another very beautiful class of examples, and that's the class of Eyting algebras. So, Eyting, the H is silent, H-E-Y-T-I-N-G, but Eyting, not hating. Okay. So, same thing, but it basically has this definition. Yeah. So, H meet join 0, 1 and implication, where H meet join 0, 1 is a distributive lattice and for each A in H, yeah, blank meet A has a right adjoint, namely A implies blank. So, we are just picking out that property. So, what is missing in this Boolean algebra is this particular form of the implication. Yeah, in Boolean algebra, A implies B can be written using negation and disjunction, negation and join. Whereas in an Eyting algebra, it's simply a distributive lattice which also happens to be a Cartesian closed category. And I mean, it will just look abstract at this moment, but in particular, you will probably identify this notation OX intersection union MT X, and what is the sorry, I made a mistake here. I wanted to say not this, but implication. Here in the signature for an Eyting algebra, I wanted the last symbol to be implication, not a negation. And what you said is, yeah, I mean, and an implication, I have to define the implication. But before that, let me explain something over here. So, for an open, for a topological space X, okay, we have a topological space, we are taking the collection of open sets. So, let us consider a simple example. Yeah, even if you don't know topology, you will understand, like if you have studied metric spaces. One important example of open subset of real numbers is that of positive real numbers. Now, if you want to define the complement of this positive real numbers, then But you can only talk about open sets. Then what will be the complement? Negative real numbers. So which property holds? If you are given positive real numbers and negative real numbers, their intersection is empty, but their union is not the whole real numbers. So it lacks the second property in the Boolean algebra. Yeah, this one, this curly property. Yeah, so Ising algebras are used in intuitionistic logic, whereas Boolean algebras are used in classical logic. So classical logic has this property, A join negation A is equal to 1, whereas in Ising algebras or intuitionistic logic we do not have that. And here everything that you do is the same. So in particular, like if U and V are, for U and V open, yeah, I still have to define what is U implies V. Yeah, this V, this thing I have not defined.
With the complement, interior of the complement of U.
Whatever you do, yeah, I mean same thing. You tell me.
Is equal to interior of the complement of U union with V.
Interior of the complement
Of U union with V.
Yes, it's take its union and then take the interior. Correct. And for U open, you can also define this negation. Negation U is defined to be,
X minus U interior.
yes, so what will be the V? So U implies 0. Okay, so U implies 0 is defined to be the pseudo complement, so called pseudo complement.
So for the first one, only V is open, not U.
No, for this line, do you mean this line?
This
I said U and V are both open.
So why do you need the U complement?
We are trying to follow this red square bracket, but at the same time we have to land inside open sets. We have to take complement of A union B. So we just did that, complement of U union V, but we took its interior. Then only we can get an open set. In general, the complement of an open set is closed. It need not be open. Yeah, so that's why. So Ising algebras are also important. Now, if your category has lot of nice structure, then the subobject lattices, subobject posets have got nice structure as well. So for example, the category of sets is really nice, and the subobject structure in that is basically a power set, yeah, and that is a Boolean algebra. Whereas if you take the category, the functor category with let's say C sets where C is small, then the subobject structure there will be that of an Ising algebra, because this functor category with small c, functor category C sets with small c, is a topos, and the internal logic of a topos is intuitionistic. Okay, so there Ising algebras will be the structure that is Ising algebras is the structure of the subobject lattices. Yeah, they are equipped with these many properties. We are going to look at toposes in a few weeks. Yeah, but for now, just understand that Ising algebras are also Cartesian closed categories. They are skeletal, preorders, everything is nice. So I will just mention at this point that there is Curry-Howard-Lambeck correspondence. Yeah, it's a very deep theorem. It is between intuitionistic logic, Cartesian closed categories, and simply typed lambda calculus. So simply typed lambda calculus is studied in type theory or computer science. Then Cartesian closed categories, category theory, and intuitionistic logic is branch of logic. So these three areas are essentially the same. That's what this Curry-Howard-Lambic correspondence says. Any questions so far?
So this adjunction is an assignment of a functor to a functor. So is
For
this,
every object, we have got this adjunction.
yeah. So this assignment, is it functorial?
No,
in the
no, no. I mean, functorial in what sense? Like if A is less equal B, then will something happen? Like here, it's just less equal.
like not there like in general in the definition above.
I have never seen that it is a functorial assignment, but I think it should be. Yeah, it's natural in all the components. Whenever we take a bijection, then it is natural in all the components. So that should be true. But it doesn't necessarily interact with the monoidal structure. Okay. Any other questions so far?
So in the definition of monoidal category,
Huh.
you have said that I is an object of C.
I is an object of C, correct?
So if we take the category of sets, we have to find the singletons are fitting as the role of I.
Singletons, like any singleton, will be the identity for the Cartesian closed structure, Cartesian monoidal structure. If you change your monoidal structure, then it will be a different object.
So depending on I,
Depending on tensor, I is defined. Yeah, if you change your structure to co-Cartesian, like co-product, disjoint union, then empty set will play the role of I. Yeah, if your operation changes, then your identity changes. Yeah, it's as simple as that. Okay, so if you understood this much, then now it's a very small trip to something slightly more involved. I already motivated these things at the beginning. So it's called enriched category theory. Yeah, so in enriched category theory, actually, what we have is we have a collection of objects, but we do not talk about individual morphisms. For every pair of morphisms, we have an object of some monoidal category as the home set. Why we are doing that? Like, let me write the definition and then perhaps it will be clear. In practice and like in literature, usually this enrichment category, the category with which we enrich, the monoidal category is called, it's denoted by the letter V. So therefore, in enriched categories are also called V categories in literature. Okay, so let me write that. So let V tensor I, alpha, lambda, rho be a monoidal category. Okay, a V category C has the following data. Okay, so now while I am writing this definition and you are reading it, you should remember the Cartesian structure on the category of sets. And then tell me what you get. Yeah, C has the following data. So V is the Cartesian monoidal category on sets. Okay, has the following data that it has a collection of C of objects, okay, for any pair A comma B of objects an object, I mean this is for any ordered pair, I should say, for any ordered pair of objects, an object CAB in V okay, then an arrow from I to CAB, it's denoted by ID sub A, I to CAA in V for each A in object of C. Then for any ordered triple ABC, an arrow, so CBC tensor CAB to CAC, and this is denoted by circle ABC in V, satisfying some conditions. Now we have to write the conditions, but tell me, what have we written so far? If V is sets, comma, Cartesian product, comma, singleton. Locally small category. Yeah, not just a category, it's a locally small category. We just have a collection of objects. Then we have a set CAB. Then we have one particular element from CAA, namely the identity morphism. And composition, like you are given one morphism from A to B, another morphism from B to C, we are getting one morphism from A to C. Yeah, so composition arrow, now it should satisfy certain properties. Yeah, it should represent composition, identity, all those things. Okay, so let's write that. I mean, the composition should be associative, correct? So let's write that. Satisfying these diagrams, so CCD, yeah, tensor CBC, tensor CAB. Okay, then here we have CBD, tensor CAB. Then over here we have CCD, tensor CBC, tensor CAB. Then we have CCD, tensor CAC, and in between we have CAD. So we are using all sorts of things. Here vertically we have an appropriate alpha inverse map, you can see. So CCD is an object of V. Yeah, so we are using associativity inverse, the associator inverse over here. Then from here to here, what are we using? 1, yes, so 1 tensor composition ABC. Okay, I am not writing 1 over what because the notations are too large, too long. Okay, the horizontal arrow here is composition BCD tensor 1. Then this is just composition over ABD, and this is the composition over. Okay. Okay, understood? So this is again a pentagonal diagram. This represents associativity. Yeah, in no matter in what order you compose, you should get this. Okay, this is the first diagram. Then there are two more diagrams, but they are sort of symmetric. So CBA tensor I to CBA tensor CAA. What is this arrow? Tell me. One tensor IDA. IDA. Okay. From CBA to I, what do we have? Well, just CBA. And this is the appropriate right identity in the monoidal category. Okay. So it's row of CBA. And over here, what do we have? We have composition AAB. Similarly, we will have another diagram. Yeah, but you can. I mean, dual is for the left adjunction. Left identity. Yeah, not on the right. CBB tensor CBA. Yeah, you can write this. Okay, so if you take V to be the category of sets with Cartesian monoidal structure, then you recover the definition of a locally small category. Okay, so let me write that down first. So for example, a locally small category is sets Cartesian product singleton enriched. Okay. So this is the first thing. Second, okay, I mean here I want I should point out something. When you look at this definition, then if V is not a concrete category, if the objects of V are not sets, then it means that you cannot actually access individual morphisms in C. You understand this? It's quite funny. So we are abstracting the notion of a category in terms of this monoidal structure. I will give you one very beautiful example by Lavere. So Lavere is metric spaces. Yeah, these are 0 infinity op, okay, then plus and 0 enriched categories. Okay, what exactly is happening here? So 0 infinity, you understand, real numbers, non-negative, with infinity as an additional. So these are also known as, I think, pseudo metric spaces, pseudo quasi-metric spaces. Okay, so metric spaces as in the home set between two elements, two objects, is supposed to represent the distance between them. The home set is the distance between objects of C. Okay, let's look at what we are trying to say. So we are given a collection of objects, and we, for every ordered pair, we assign a real number. Yeah, because object CAB is an object of V, but V is 0 infinity. Okay, and an arrow. What is the meaning of an arrow? So I said 0 infinity op. So arrow, like there is an arrow from R to S if R is bigger equal S. So what does it say? Yeah, I mean, so D of an object A is bigger equal 0. This is the identity thing. And finally, the composition, yeah, what is the monoidal operation? It is sum, where infinity plus anything is infinity, right? But there is an arrow from here to here, which means the left hand side over here is bigger equal this. So that becomes the triangle inequality. Okay, so distance from B to C plus distance from A to B is bigger equal distance from A to C. So that's why these are called pseudo quasi-metric spaces. Of course, not all properties are being satisfied. Sorry, I think I made a mistake here. I should have said 0 is bigger equal this. For any ABC in the enriched category. Okay, so I'll give you some more examples, like AB is self-enriched. What is the meaning of self-enriched? So that's what I started with, yeah. Abelian groups, the home sets in abelian groups, they carry an abelian group structure themselves. So this, yeah. Similarly, the category of R modules is self-enriched. Sorry, is not self-enriched, I want to say, is ab-enriched. Such categories, i.e., is pre-additive category. So this pre-additive category, additive categories, abelian categories, yeah, that's going to be our next lecture. Okay, another example is POS is also self-enriched. With respect to the Cartesian monoidal structure. So one comment to make here is that any closed monoidal category is self-enriched. Okay, because there is internal home. Yeah, that internal home will behave nicely. You have to work out this example properly. Any questions? Okay, I'll just give you two simple things. Yeah, I mean, if at all this category V, the monoidal category V is concrete, then you have the home sets are actually sets with some additional structure and some additional properties. Yeah, I mean, how do you capture something like that? It just one line. So if C is a V1 category, V1 enriched category, or V1 category, just yeah, and D is V2 enriched and F from V1 to V2 is a monoidal functor. I can also write strict, but it's not necessary. Then C can be thought of actually D is also not really necessary here. If C is V1 enriched category and F is, let me directly write F from V1 to V2 is a monoidal functor, then C can be thought of as a V2 category, means V2 enriched category. Yeah, in particular, if V is concrete, what is the definition of concrete? There is a faithful functor to the category of sets. Okay, that is a monoidal functor. Yeah, if with a monoidal forgetful functor, faithful functor, U from V2 sets. What is this functor? I can also write it Vi blank. Yeah, representable functor. Then any V category is a locally small category. With additional structure on home sets. So this fact is really important. Yeah, we are going to use it in the case of pre-additive categories. That we are given an AB enriched category, a pre-additive category, and then the home sets have got an abelian group structure and composition is bilinear. That composition is bilinear is important. Yeah, its home set is a set with additional structures which behaves nicely with respect to composition. Understood? Okay, and there is also a notion of enriched functors between enriched category. Like if you fix V, then and there are two enriched categories, then you have a natural notion. I'm not going to write down the definition of an enriched functor. You can check it for yourself. Any question?
So, sir, you have said that any closed monoidal category is self-enriched.
Yes.
So, is there any self-enriched category which is not closed monoidal category? Because you have given in the first three, for example, which are closed monoidal category.
Okay, I do not know it on top of my head. Sorry, I will try to think about it and tell you next time.
So how is Vi blank of the forgetful functor?
Yes, in that case it can be thought of as it the set of this V is a category. This the forgetful functor is a representable. Isn't that mostly true? Groups, yeah.
This is true in any monoidal category.
No, I'm saying if this happens, if this condition happens that Vi blank is the monoidal forgetful functor down to the category of sets, then this happens. Yeah? Okay, let's stop here.